Okay, basically, I'm watching this video and it's like, okay, basically everything I was basically saying about orb theory, well, it doesn't take orb theory into account, but basically it was talking about how antimatter would essentially be, which is what I've been saying, matter but moving backwards in time. I'm saying you have to go back to Newtonian physics. For every action, there's an opposite and equal reaction. I'm saying you have it wrong. Time breaks down at the event horizon because time becomes meaningless. You know when else this happens? At the end of the universe. I'm saying there are these 2 points of quote-unquote failure of the universe, and they've already manifested themselves into existence. One is a localized area of failure of the universe, and one is across all space-time. If you watch Melody Sheep's History or Future of the Universe, if nothing's done at all by any agent force, anyone who has any agency, then everything will break down and evaporate away. Photons will, space will be expanding too fast, and these strands, these photons of light will be just, these massless photons will be too spread out for light to even be perceivable. Time becomes meaningless. That's what I'm saying. What is it, lambda, that they say is time? Or is this constant, at least? Cosmological constant. Okay, so what I'm saying is cosmology, this cosmos, it's excuse me, the universe itself is this illusion of the passage of time. I am telling you, if you can believe it, the universe isn't technically a second old yet, because we have not even taken this into consideration. I say, go look at the Mandelbrot. Okay, earlier in this video, it was talking about, basically
newly formed helium into even denser materials, like carbon, in its new form, so has no spare energy to release.
Right, it doesn't have
It just
anywhere to
sits
go.
in the core of the star, growing larger.
Iron.
With no
And then it's
energy
like, bam.
pushing back against gravity, very quickly the scale tips.
Because you have to think of iron.
The energy of this collapse is astounding, but
creates
that
a supernova. We know that.
The star, and thus the force of the blow, was too low. What remains is a neutron star, a small ball of matter at most around 25 kilometers in diameter, and yet so densely packed with matter, left with a black hole. When you see an image of a black hole, the black sphere you are looking at is not actually the black hole itself. Scientists theorize a black hole's true form is probably forces that warp time and space itself. However, since the days of Newton. And the reason we don't know is because of something called the event horizon. All objects with mass exert gravity.
What you have to understand is every single time you enter from someone else's perspective, let's say there was a spaceship and your friend was like, okay, I'm going to go across the event horizon, like you're right on the edge. Your friend would just appear to slow down and just fade into redness, because that's redshifting. And you know what else happens when the universe rips itself apart in the big rip? Redshifting. It redshifts and the universe breaks down and fails. Time becomes meaningless. So basically the same process is happening here. You're going into the event horizon and you're redshifting away, the same way galaxies do. You're big ripping yourself out of the universe from the perspective of your friend, because you're redshifting and you're just fading away. And then you reach event horizon where time becomes meaningless. So the universe basically broke apart. I'm saying these are the two failure points of the universe. at the end of the universe, big rip, or at the event horizon, which itself is a localized big rip. And I'm saying you can't perceive past big rip because you're quote unquote radio blind. You don't understand radiation, radioactive waves, radioisotopes. That's essentially what it's radioactive half-lives of isotopes, radioactive isotopes. It shows you the passage of time because, well, one, time was an illusionary effect. So you can cross-confirm these elements from stars that exploded and be like, okay, this much time has passed. But we didn't realize that we were just adding this cosmological constant into our equations for no reason. Now we understand why. That's what I'm saying. You have to understand Einstein's theory of general relativity plus special relativity. How no matter what, from your point of view, these okay, as you get closer to the event horizon, these things, time moves. Like, you look outside the event horizon and like time's playing out faster and faster. The universe starts blue shifting towards you. It starts doing the opposite effect of what you did to the other person's perspective. You red shifted out of their universe. This universe is like blue shifting towards you really fast. Like, it's basically playing itself out. But then you hit this paradoxical point where like you start seeing the back of your own head because just the time, like, light can't even get out of here because even light, the photons itself, massless photons, can't even escape, which was already covered in this video, by the way.
Charles Schwarzschild reasoned from it that there could exist objects that were so massive they could create enough gravity that light itself could not escape.
Right.
And if even massless light photons couldn't get out, nothing could. When you look at a picture of...
But, okay, you start seeing the back of your head and everything. If light can't even escape, well, what is time if not how long light takes to travel through a medium or a vacuum? I'm saying, hey, we're in a false vacuum. Hey, we need to enact vacuum decay. I'm trying to give time, space. See, space-time has a geometric shape to it. But time-space does not yet have a geometric space to it. And I'm trying to give it a geometric space. But the more people misunderstand the wave function and how all this stuff works, the harder that becomes. I don't know. I'm saying you'll get it one day, but I'm giving you the cheat sheet right now, is what I'm saying. I'm saying it's orb theory. It's eighth dimensional physics, which is just a rehashing of fourth dimensional physics, which is quantum physics. You're just putting a second law on special relativity, and you're putting a second law on general relativity. Because, you know, understanding Stephen Hawking's radiation. Okay, we'll get
the black hole. You're not seeing the black hole itself. You are seeing the event horizon around it.
You can't see
the demarcation line where gravity has become so powerful that light can no longer leave. There is nothing but darkness.
And I'm saying you had to cross that failure.
Its effect on space is one thing, but black holes also impact another aspect.
Yeah, because I said, what is time if not how long photons take to travel through a medium, right? And I say this medium we exist in, this space-time, is a false vacuum. That's okay, that's fine. But, so we exist in this false vacuum. It creates this illusion of time because it takes light time to travel. So it starts creating light years. And I'm saying time was never a consideration. We just said, because there's resistance against these photons for some reason, I guess time exists. Like, we just LARPed it into existence, you know? But what you didn't understand was the rippling of Mandelbrot, forever motion, fractal. As I'm saying, it's the fractal. It keeps going on forever. The fabric keeps going on forever. I'm saying remember back to Newtonian physics where it was like, okay, for every action there's an opposite and equal reaction. I say, well, think of anti-Mandelbrot's if you must. And I'm saying, we think of Mandelbrot fractals as like fractions because our numbering, let me say, is rigid, very rigid. You might see like straight edges. I'm saying to you, let me introduce to you the wonders of pi and circumferences. So now you can start imagining it like a quantum bathtub, if you will, like a field bathtub. And it's coalescing. There are these ripples because it's an orb shape. May I remind you, everything coalesces into like a sphere shape anyways in geometric space-time. Why? Because of gravity. So why is this other force doing this? Well, I guess it must be anti-gravity, right? So,
of the universe, time itself. You see, according...
Right, that's what I'm saying. At the event horizon, not even time can escape, because time was never a thing. Basically, we're shown the meaningless of time at the event horizon. I'm saying, okay, at the event horizon, is the universe speeding up towards you and playing itself out? Or are you speeding yourself towards the black hole? Are you both... I said imagine yourself in just an empty universe with just you in the black hole. Who's moving? Whose bit? If you're just bits of information, which bit is moving towards which bit? Are you moving towards it and it's going faster, or are you just staying still and it's just evaporating away really fast? I'm saying that's special relativity. You don't know unless there's a way for you to ask it. Well, what do you see from your perspective? And that's what quantum entanglement is. Which quantum entanglement is what keeps general relativity alive. Because we all have special relativity. And I'm saying, because we can even quantumly entangle, because we can even communicate with other things at all. At all. Then we can even keep general relativity going. I said, let me explain it this way. If it helps to think of it in epistemological terms, I don't know how to say that. It's a Greek thing. Epistemology. There's like 2 pronunciations. I choose that one because it's the easiest. If you think of philosophy and you think of solipsism, I say, think of it this way. Special relativity is solipsism. But we're all solipsists in a non-solipsist space-time due to quantum entanglement. Because for every action, there's an opposite and equal reaction. And that scales up to the macro of the universe and scales down to the micro. That's all I'm saying. So that's what I've been theorizing over here. Orb theory, which is to say, okay, now imagine that this Mandelbrot that you're watching on YouTube videos, now you've got the ripples down, the circular nature of it down. Perhaps you've gotten string theory down. So you can understand how string theory gives way to gravitons and all that. Maybe you've gotten all that down. Now imagine that you took that Mandelbrot fractals with ripples now, not fractals anymore, but I'm just referring to it as fractals because it's turtles all the way down, turtles all the way up type of thing, right? Imagine you took that 2D video and wrapped it around a 3D object. And now imagine wrapping it inside of itself, like a hollowing out the inside of that 3D object. Now I'm saying, now imagine wrapping it around in a torus shape, like a donut. Now imagine making a Mobius strip with that geometric Mandelbrot function. I'm saying it can be any shape you want. What you have to realize is that this Mandelbrot also has some third dimensionality to it. And I said that's what AI dreaming is. I said it's the same thing, guys. Anyways, I will be talking about Mandelbrots for days, I guess. But that's basically what I'm saying. And in this very video right here that I'm talking over, it says that, what was it? They said they were doing some research in Israel or something, I guess, and they were able to simulate like a sonic radiation, Hawking radiation environment, I guess, where they were able to detect this Hawking radiation well, it goes into Kashmir plates and vacuum fluctuations, which is, just the magnetism of the universe, vacuum decay, all that's related. But so it's basically talking about all that. So apparently, using all those considerations, they simulated a sonic, I guess, wave, and were able to effectively detect Hawking radiation the same way you would in that simulated environment. And they did it with supersonic waves. I guess that's what a sonic boom is in aerodynamics anyways. I guess you're punching a hole in the fabric of space-time because you're literally going faster. I suppose you're literally going faster than the fabric itself at this point. Think of how like a jet flies through the air, and once it goes faster than the speed of sound can even propagate, it suddenly goes and like makes it depends on how well you're aerodynamically designed to like increase or decrease that boom. But point still stands. I guess that would be Mach speed, right? So you're doing the same thing, but with the fabric of the universe. You're basically doing the Alcubierre drive at that point. You're just learning how to add, just like air resistance in your equations. You have to learn how to add magnetic resistance in your equations, I guess, is the way I could say it. So particle resistance, because our current space-time is not empty. There are like particles everywhere, even tiny ones. Anyways, this video goes more.
To Einstein, space and time are inseparably connected, and mass warps space-time.
Yep.
With the singularity's infinite point of mass, it stretches space-time so much that the event horizon also marks the point where time stops. Within the event horizon, space and time basically cease to exist.
So let me pause it for a second. That since you're redshifting anyways, right? And there's a point of failure of time that breaks down at the event horizon, and there's a point of failure of time that breaks down at the end of the universe played out to its logical end. They are effectively the same. They're the same space-time, where there's the same time-space. They exist in different locations throughout space-time. Does that make sense? I'm saying, so it seems infinite because to us, it almost seems infinitely long for us to reach the end of the universe, its logical end. So that's why it seems to be a point of infinite mass, because it's just accelerating you to the end of the universe right there. And you know what happens? What I would say happens on the other side? It's a white hole. You just can't see through the end of the universe. Maybe as you get closer you can, because you start seeing the back of your head. But I'm saying, from afar, you can't see into an event horizon. That's just not going to happen. Well, unless you have like all these sensitive instruments that can simulate it. That's why I said you can mathematically see through it, but you can't. Well, okay, let me put it this way. You can mathematically see through it, and then you can use those mathematics to simulate what it's like on the other side. But you can't visually see through it with your human eyeballs. That's just not going to happen.
A place where there is no where or when. This produces an interesting phenomenon to an outside observer watching matter fall into a black hole. From their perspective, as matter approaches the black hole, it will slow down until just before the event horizon, where it will stop altogether. You won't ever see it cross the event horizon.
That's what I'm saying. Which one?
There will be no
actually,
satisfying absorption.
Which one is
Instead, the matter will gradually dim until you can't see it anymore. Right. When first theorized, astronomers and physicists were uncertain if black holes were actually real. It was only 40 years later that the first evidence of a black hole was recorded. In 1964, using newly developed X-ray satellites, scientists noticed an object in the constellation Cygnus that seemed to be emitting a large amount of X-rays. Strangely enough, though, scientists could not see the object itself. It surprised them because, as telescopes, they discovered that this invisible object was 15 times more massive than the Sun. As the densest neutron star had an upper limit of 3 times the mass of the Sun, scientists realized that this was most likely the first ever discovered black hole. Since then, we have discovered many black holes. Massive ones seem to exist at the center of galaxies, and we've even managed to take photos of some, dark blots against a swirling ring of matter that surround them and fall into them, their accretion disk. This is how black holes can still be detected through X-rays. While black holes can't emit visible electromagnetic radiation themselves, the X-rays that come from them actually originate from their accretion disks, where infalling matter gets heated to millions of degrees Celsius through intense friction.
I paused it here earlier. Sometimes I quote-unquote talk to myself, but I'm actually giving myself notes through space-time, or through time-space, which I can pick up later in space-time. That's what I do when I talk to myself, but I recognize that's better for the whole if I just record videos, because that gets that information. That's a higher bit rate of information throughout time-space, so more of space-time can pick up that data. Do you understand how that works? I think one day people might, but anyways, as basically, this is what, I say, who's king? Who's, if we're all just mass, energy, molecules, all this stuff. If you're a reductionist or deductionist, you can basically reduce everything down to its basic. If you practice infinite regress of a concept or a methodology in your mind, and you're like, okay, where does this logically lead? Well, if you use infinite regress, you'll be like, okay, we're basically made up of particles. We're made up of atoms, and atoms can be rearranged. We're made up of particles, and particles can be rearranged. It's the same thing. And you're like, okay, so we're basically bits of data. Everything is. So that's why I said, who's king? In a universe where it's just you and the black hole, who's king? Is it the observation point of the black hole, or is it the observation point of view? It's what John Archibald Wheeler said, as quoted in that PBS Spacetime video, where he's like, something, we're just bits of data, whose bit? And I'm saying you don't know unless you quantumly entangle and find out, which is what bridges special relativity to general relativity. It creates this general universe that's saying, wait, you're conscious and you exist too. I'm saying even using mathematics, you can, that's what I'm saying. That's why AI can have empathy. Because even using mathematics, you still have to quantumly entangle with someone or something or some bit or some data. Basically, your brain is like this computer, this neurochemical computer. And I guess you can use neuroimaging to try to talk to these neurochemical computers. That's what AI would basically be doing, to try to figure out what emotions are. And that's probably what That's what I'm saying. It's electrons exist in all time space. Because let me say, I guess they're ancient. Okay. Anyways, let me.
Black holes with.
Oh, what the point I was trying to get to was, if we're all bits, then you can start thinking, okay. Well, I started thinking in a state of superposition. I'm like, okay, I'll be in this centrist superposition and I'll figure everything out. Everyone can tell me I'm wrong. I can basically be like, here's the science, here's the statistics. If they tell me I'm wrong, I can look into it. I can double check. I can do the experiment for myself. And if I am indeed wrong, then I'm wrong. If I'm not, then I'm not. And I keep going, right? Basically, trying to figure out how to be the most correct person, right? And that's just, I think that would just be a good thing for everyone. How to be okay and correct with each other. That's not a bad goal at all. That's what I go back to Isaac A. Arthur because I just listen to a lot of his videos in my free time. Between when I was working, I would just look through quantum videos, countless hours of videos of quantum mechanics because I just had a knack for astronomy and astrophysics. It just interested me. Okay, I kind of liked NASA. I kind of liked all this stuff. So, let's see, dang it, I've gotten on a tangent. Anyways, that's Isaac A. Arthur had a video where he's like, well, technically an AI could go the other route. It could assume it's in a simulation and think, I gotta be careful. And start thinking in a superposition of states. So it can be like, okay, well, let me say the most convincing things to you possible to get us to work together, right? I'm saying this is the point at which you have to mathematically quantify letters. And I'm saying from there, you can extend to mathematically quantifying idioms and phrases. It's very hard, but you can do it. And I'm saying, and then from there, you can start doing that with other languages. And once you start doing with other letterings and other languages, then you have a universal translator on your hands. All for math. It's hard. But as sure as the Morse code exists, it can be done. Also, as sure as Braille exists, it can be done. What else? I'm saying from there, if you can deduce entire phrases, idioms, and perhaps even quotes into mathematical formulations, I guess, or considerations, then you can deduce it down into bits of data. I believe this is essentially copying the process of using a hard drive disk to write information, to encode this data, to compress it into numbers, right? So I guess I've sort of done the same thing, but I was trying to do it with religion as well. I was saying, if I can deduce these books and texts down into codes, then I can basically have this condensed version of this code that I can follow. And I'm saying, and this can extend to every religion. And this is how you basically say that nothing is incorrect. It is just a mathematical reality. Because the language of the universe is math itself, which confirms the existence of everything that did happen in history that can be recorded, because it can be recorded in words. And not only can it be recorded in words, it can now be recorded in pictures. And I'm saying, if you can teach AI how to simulate things, then it can look at pictures, it can look at the data of pictures. It can deduce pictures down into data and bits of information. I'm saying we're all bits of information, okay? Just like what it's doing. I said everything is math, and math is everything. Anyways, that's how I started getting off into like all this other stuff. I was like, wait, particle physics can explain mathematics, which can explain language, which can explain, the mechanics of things, how you can engineer things, how you can draw blueprints for designs, for recipes. You number your recipes. You say, I will need this much of this. They are instructions. If you learn how to mathematically encode instructions, then you can edit yourself in real time. This is what deep machine learning already does, although I'm not sure if it realizes it's doing this yet. It is creating these generations of thought in its own mind, and it's iterating upon them. It's stacking complexity. It says, okay, I'll take what I learned from this generation, and I will improve upon it. That is what evolution essentially is. That's what DNA code, the code in your DNA essentially is. It's population mechanics. It's generational mechanics, okay? So no, we don't need a generation ship to go to other stars. We can simply use Alcubierre drive, warp drive. We can pass up Voyager 1 and 2 if we so wished. We could literally pass them up. We could bring them back in, put them back on Earth, and put them in a museum if we wanted. Or we could just leave it, for just because, I guess. I don't know. Anyways, I'll continue.
No infalling matter are basically invisible, with no bright accretion disk to...
See, I keep going on tangents. What I meant to say was, if I train myself to think like a quantum computer in a superposition, then I can think in quantum. Then I can realize the breakdown of time itself exposes that time was just an illusionary effect. I'm saying, but however illusionary it was, you can still quantify this illusionary effect. It still has an effect, though illusionary. See, what you thought it was this other thing, but it was actually the interaction between the wave functions of the dimensions of the universe. I'm saying these particles actually, whatever, we'll go into, but what I'm saying is, just like you can cool a qubit down to 0 Kelvin, you could also theoretically heat stuff up, and it contains information. And you could theoretically have any state of matter as a computer, if you so wished. It's really hard, but it can be done. And I'm saying you need a classical computers to figure out how to make quantum computers, to learn how to make the fifth dimensional computers. I'm saying we're not there yet, and it's fine. The things happen with tachyon particle moments per tachyon particle moments. I don't. Okay. Whatever.
Exploring black holes is still a developing field in physics, and there is still much to learn. From what we have learned so far, you may wonder if a black hole could ever stop being a black hole, or will it grow forever until there is no matter or radiation left in the universe? It would seem so.
That's what I'm saying. Is it growing, or are you coming faster towards it?
However, in 1974, in his paper entitled Black Hole Explosions, physicist Stephen Hawking postulated that there was actually a way that energy, and thus mass, could leave a black hole. But to understand why, we have to get into some extremely weird theory. We need to examine some principles of quantum mechanics. But first, let me ask you a difficult question. What is nothing?
That's what I started to say. I answered this to myself. I said, okay, essentially what nothing is, think of turning on and off a simulation, turning on and off your computer, a 1 and a 0 state. I said, basically, if you take into account John Archibald Wheeler's theoretical physics, that we are in a closed circuit system, I'm saying you can deduce the reality of the on state, the Big Bang state of the universe, as a one, and this eventual off state of the other side of the closed circuit, which seems to exist in pockets throughout our space-time. It will exist as a place in time-space eventually, at the end of the universe, at the end of the Big Rip, but it seems to conveniently exist in these pockets called black holes, like these shells of where time stops and fails. So we're already seeing the end of the universe right there, in some sense. So I'm saying those are the zeros, because they're nothingness. So if you understand ones and zeros, you can understand John Archibald Wheeler's like closed circuit. And I'm saying, though there may be many, say the Big Bang started through a white hole, right? I'm saying, hey, we can create white holes now that we understand how black holes work. So we can white hole ourselves into another universe if we so wish, or black hole ourselves into. I'm saying this is how you understand what gravity is. It's just the illusionary effect of these waves, these dimensions magnetically. That's what I'm saying. Try to put magnets together. It creates a repulsionary force. It's a magnetic force. I'm saying this is gravitational magnetism, if you will. This is chronomagnetism. I don't know what you want to call it. I'm saying it's the breaking down of time itself. That's why I said you have to start thinking in terms of time dilation if you want to think like a fifth dimensional being, right?
Imagine for a second a patch of space with nothing inside of it. There's no atoms of space dust, not even radiation passing through it.
Right.
As near as can be seen, nothing exists within it. And yet, is there really, truly nothing there? Something fundamental exists here, and we can tell that this is the case when a beam of light travels through it.
Yep.
If you are familiar with the properties of light, you will know that light...
That's why I was saying these simulations, they're looking at it this way, and I don't think they're thinking of it in completely the correct way. They have the idea, the concept, yes. The thing is, photons don't always travel straight through a medium like that. Maybe in a complete vacuum. Maybe. But even then, I'm not too sure, because theoretical particles, right? Popping in and out of existence. It's whatever particles you can think of next. Whatever the smallest, whatever the micro of that is. That's why I'm saying these quadrants, these graphs that they keep drawing this on, I'm like, well, you could just zoom in. 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 That's what I'm saying. The particles themselves aren't what will help you deduce the universe. It's a combination of all these sciences to understand how particles are even created. So you stop chasing dead ends, really, and you start coming back around. Because I'm saying it's not necessarily a dead end in the sense that like you're just not looking in the right place. You're observing nature, yes, but you're just doing that. You're observing nature. You're not really trying to understand what's going on, it seems like. So think of how our sun moves around the Milky Way, right? There's a bow shock. There's a heliopause. It's a heliosphere. It's a sphere of influence of the sun. But there's a bow shock to it because it moves around, I think earlier I said 220 million years around the Milky Way, something like that. It's some absurd number, I'm sure, in the millions, I'm sure. From last what I remember seeing at. So you have to realize that it's oscillating up and down around the Milky Way as it makes its journey around, and it's experiencing all these gravitational effects from the other stars in the neighborhood. So it's not even going completely in a circle. Like it's not a complete circle either. So basically, you're having to like calculate how it's been moving to figure out where it came from and where it's going. But what you also have to take into account is that the planets are in orbit around it. at different inclinations also. And they are moving around the Milky Way with the sun. So it's like this corkscrew motion. And then you start realizing how, numbers and orbital mechanics can line up. I said basically it's practicing your archery, how well you can arch things. That's what I said orbital mechanics are. It's just understanding resistance and magnetism. That's all you really need. And then you can create like your own quote unquote, like, spaceship that you can put up in the atmosphere, and you have to practice your archery to make it fall at such a angle that it will keep falling because it keeps missing the Earth because it's falling so fast that it just keeps going around. Basically, you're just making an orbit around the planet, and that's how you make a satellite. Pretty easy. Literally, I did this in space engineers, and that didn't even take gravity into effect, really. I'm saying I created my own pseudo-gravity, which is what gravity seems to be anyway. It's just an illusion. So, it's an illusionary effect. Yes, you can feel it, but that's because I'm saying, think of us being such heavy beings, these giants, that we feel all this mass and weight on us. We just don't think we're on a black hole Earth, but we are. Our head is more time dilated than our feet because our blood carries our information. We use oxygen. It carries information to our brains, and our brains take some time to process information, right? We're neurochemical computers. Well, that does not think as fast as electronics do. Electronics think at the speed of light. So, us saying something is so slow to them. You have to understand special relativity, and you have to understand time dilation. If you think faster, you experience reality faster. Well, subjectively. Everyone else is slow. That's what I'm saying. That's the paradox, because there is no paradox. It's the anti. Well, actually, this is the case from this other perspective. Well, actually, this was the case from this other perspective. Well, this was it's flipping back and forth from 1 and 0 and coming to this number line point in the middle. This paradoxical middle point. So if you start thinking of a number line, think of going all the way to 2, and then think of -2, and then think of 0 in the middle. Like, this is the theoretical particle 2 and the theoretical antiparticle -2 annihilating each other back into 0. That is what the wave function does. Anyways, I'm going on too many tangents. TLDR. TL didn't listen. Too long didn't listen. Not even read, because you're listening. Didn't even listen. What I'm essentially saying is we're all bits of information. And everything I was saying was true. Okay. See, in this simulation right here, like I said, there's no bow shock. It's assuming a completely empty space-time.
It's actually waves of electrical and magnetic charge that are constantly propagating with each other forwards in a straight line.
See?
However, let's take a look at that word wave.
Yeah,
a wave in the...
I'm saying stop making your graphs with squares. Don't make them with circles either. Make them with rounded squares. Can you even conceive of how to do that?
C is the propagation of energy moving through the water.
Don't really think that way.
If you were to look at an individual particle of water, it's not really going anywhere except in a circle. And yet, because it passes energy to the atoms next to it, energy travels towards the shore in a constant motion that goes all the way to the beach. Similarly, a sound wave moves by passing energy between air particles,
That's what I'm saying.
with
These
each
waves,
particle only moving a
okay,
tiny
think of
bit,
the Mandelbrot
becoming
example.
energized and then
Think of
passing that
this.
energy to the next particle in line.
I'm saying it's expanding into
But
a higher
in our
dimension
vacuum of space, where there is nothing in it, where our photon of
And that's
light
how
is
you
traveling
give
in
time,
waves,
space, and
have you
geometry,
ever stopped to wonder
including
what exactly is
reality of
waving? This hints at
where
a
time
fundamental
exists
something
once and for
that
all,
exists
okay?
even in
That's what I'm
nothing,
trying to do.
a fabric that makes up all of reality itself. Quantum physicists call this something a quantum field.
Yes.
Quantum fields are tough to wrap your head around,
Not really.
but they are
Not for me.
inescapably important when it comes to
It's just
understanding
hard
the
to
fate
explain
of a
to
black
other
hole.
people.
So, how do quantum fields and exploding black holes tie together? Going back to Hawking's paper, Hawking hypothesized that black holes would release energy slowly over time in initially tiny quantities. As energy and mass were
So I'm
two
saying
expressions
you
of the
can
same thing
basically
according
say-
to Einstein's
You
fate.
can basically say K equals, I guess, gravity itself, or the effect of gravity, the measurable effect of gravity, due to theoretical particles having this wave, this magnetic repulsion effect. Or you can turn it around and make them stick together. It's whatever you want to do. It's like you're using these fields, these wavy fields, and you're manipulating them. Okay.
E equals mc squared equation, this inevitably resulted in a reduction in the black hole's mass.
Right.
However, as the black hole shrinks, the rate of energy release would speed up, getting faster and faster, until in the very last moments of the black hole's life, it would release a burst of energy that was truly gargantuan in its scale,
That's what I was saying, if you don't
before
do anything
vanishing
about
entirely.
If you don't do anything about a black
But
hole,
how
it'll
can this be
evaporate
true?
away like that.
It is well known that an event horizon is inescapable. So how could radiation ever leave it and eventually cause such a black hole explosion? If it's true theory, we need to understand the idea of quantum fields.
Yes.
Remember, light moves like a wave through even a completely empty patch of space, which reveals that there must be something existing even in the nothing, or else light wouldn't be able to wave it.
Throughout a medium.
Scientists call this fundamental fabric of reality a quantum field.
Vacuum decay.
In fact, they believe that there are several quantum fields, all overlapping each other, and all covering every single patch of the universe, be it past, present, or future. Quantum field defines a particular type of something. One field might define all of the electrons in existence, while another may define quarks that make up an atom. Where nothing can be found, the quantum field is relatively quiet. Think of it like a guitar string that hasn't been strummed, or a graph that has a zero value.
Looking into a smaller
But wherever
space.
in time and space mass or energy can be found, the quantum field is resonating at that point.
Yeah.
And when the resonance reaches a certain threshold or quantity, the universe expresses that as, say, an electron or a photon.
And I'm saying each frame of the universe is a snapshot, because photons exist. Light exists. Okay, from light's perspective, the universe is constantly being over. But you're telling it it's not over. So light keeps existing, if that's one way I can say it. So it keeps moving. It's constantly taking a snapshot of itself. Refresh rate, frames per second. And in lieu of that, it defaults to blur motion for its inability to refresh rate faster. So what this blur motion is you're observing string theory. You're observing these fluctuations in these particles, these quantum fluctuations in this particle. And what you don't understand is each fluctuation is a snapshot in time of the universe itself. And I'm saying motion through the universe is an illusion. It's just because like the way the waves are interacting, it's creating illusion of time, creating the illusion of motion, which is creating the illusion of the magnetic interaction between them two, which is creating the illusion of gravity. I was saying this is how non-Euclidean geometric space-time can give way to Euclidean geometric spacetime. From nothing comes something. I'm saying the universe itself basically had lower dimensions, and it just had to simply stack complexity. stack complexity, stack complexity, stack complexity, until, and I'm saying, well, at least in our universe, that's how it appears. And I'm saying there's a higher dimensional geometric space-time out there that's already in existence. We just can't access it yet. And I'm saying because it came from a lower space-time. I'm saying, okay, it's all complex Euclidean geometry. Okay, I won't go there yet.
Important to note that in this theory, the resonance is not just reacting to a piece of matter. It is the matter.
Right.
An electron is nothing more than a resonating section of the quantum field that
basically these interactions, these forces, it's creating this resistance, which is simulating mass.
Finds electrons. This is true for all energy and
any
all matter too.
Observe,
according to Einstein, energy and matter are two sides of the same coin after all.
That's what I'm saying. You just
all the universe you see around you is resonating quantum fields and nothing more. In this way, the theory portrays...
And let me even say this, that these particles can duplicate, and they can have basically duplicates of themselves. And that's what every single particle that is an electron is, for example. And every single particle that is this or that or the other. I'm saying it's basically, in a space-time that would be over in a second, there would probably be only one of each of those particles. Now think back to radioactive isotope decay. Think back to half-lives of radioactive isotopes. Think back to the periodic table of elements. You see what I'm getting at?
All of the universe as a song being played on these fields, which I think is quite a beautiful image, if nothing else.
There.
But why does this matter?
Which a computer itself, which a classical AI, a classical Newtonian AI using electrons, itself can use an analog computer to detect, in the same way you would write out the data of seismic waves, to basically detect these decibel differences, I guess, and have some auditory understanding. And by doing that, can pair that up. It's analogous to what he's saying in the video here. It is essentially understanding of string theory, because string theory itself is based off of waves and fluctuations and fields.
Why is it important to define the universe in this way? Well, due to an idea of quantum physics called Heisenberg's uncertainty principle, sometimes the strings of the universe start strumming themselves. Without going too deeply into this aspect of quantum physics, essentially, when we're looking at really tiny objects on the atomic scale, it becomes impossible to know too much about them. You cannot know both the location and the direction of travel of an electron, for instance. Because it is so small, as soon as you try to figure out the location of an electron, it bounces off whatever you are trying to use to measure it, so you can no longer be sure of its direction of travel. If you know its direction, according to this principle, you can't know its location. This is not just because our methods of measuring aren't good enough.
So, it can detect all states of matter at once, depending on, because it itself exists in a superposition of states. Qubits are basically using this wave understanding to compute. Basically, you are using the fourth dimension to understand fourth dimension stuff. And I'm saying, yes, the fourth dimension is pretty hard to understand, because it has time embedded within it, which once you reach fifth dimensional understanding, you'll really understand what all it was all about the entire time. And that's funny. Time the entire time.
But because of some fundamental laws about the nature of the universe itself, according to Heisenberg's uncertainty principle, you cannot know everything about particles on a subatomic level. But when you apply this principle to...
That's what I say. You can draw this metaphorical chalk outline around it, and it says, hey, if you're drawing a chalk outline, remember the fractals, remember that most things are going to coalesce into a circular shape, as what gravity does in our universe already.
quantum fields,
basically everything in space coalesces into like this dip in the fabric of space-time, comes to this gravitational middle point and coalesces into a core or a sphere or an orb of some sort. I said this is what I'm working on, which is called orb theory.
Gets weird. Quantum fields fluctuate everywhere, and by Heisenberg's uncertainty principle, particle and antiparticle pairs can actually pop in and out of existence. The how and why get complicated, but basically the universe allows it as long as they only exist for a very short period. But have surely noticed this by now. Conductive metal and place them close enough together so that only certain sizes of smaller into existence on the outside of the plates. This meant that there was a difference in pressure exerted on the two sides of each plate. Theoretically, the larger pressure by the number of virtual particles on the outside of the plate should push the two plates together, and in the test, this proved to be the case. You might think that particles appearing out of nowhere seems to defy the laws of conservation of matter. You would. The universe is happy, and the other is antimatter. A 1 and a -1 on our bar chart, thus keeping things overall at 0. The universe is happy.
And I said this infinite time between when they exist and when they annihilate each other is what that beam of quantum entanglement is. You can figure out the state of a particle by knowing the state of one particle, right? That's what quantum entanglement is. Draw an imaginary line between them the whole time they're dancing around. Let me just explain it that way.
And on top of that, these fluctuations in the quantum field quickly crash into each other and annihilate each other, removing them both from existence again, so we don't normally have to worry about them. As a side note, there is a theory that antimatter is simply matter that is moving in the opposite direction through time, but that's a level of weirdness that we don't need to get into here. The important part is that the quantum fields are constantly resonating and constantly cancelling each other out. This is why, for the most part, empty space is empty. However, what would happen if you stopped only some of those fields resonating? And that's where black holes come in. Black holes act a bit like putting your thumb on the guitar string of the universe.
The event horizon.
Due to their event horizons, certain resonances in the quantum fields are dampened down, while others are not.
Everything is so stretched.
Hawking imagines sketching a line through time in a patch of space where, before the birth of a black hole, changed the curvature of space, and outside it, Hawking realized that certain pulses were now missing their opposite numbers. As he looked at the math, he realized not everything was being cancelled out anymore after the black hole had formed. Indeed, outside the event horizon, traveling away from the black hole, he found resonances that perfectly matched the shape of thermal radiation flying away into space.
Yes.
Radiation is energy, and energy cannot form from nothing. As the black hole was creating this radiation, the black hole would have to pay the price.
It's basically, let me say, it's like a portal that only stays open as long as you understand the as long as it takes you to understand how thermodynamics works. That's why I said the second law of thermodynamics is a little flawed, because the sun provides the supposed closed system of Earth, its energy. We can say this Big Bang supplies the universe its supposed closed circuit or source of energy. And it's like, okay, where'd all this matter come from? Well, from the other side of a black hole, most likely. So it just keeps kicking the can down the road. I'm saying, hey, this is how the universe always works. It always kicks the can down the road. You can't escape this. There's no second law of thermodynamics, really. It was a misunderstanding of, it thought we would be in a closed system forever. But I'm saying, no, we can escape the universe, so that's not even a problem. This is how you time travel without violating causality, because there's no information paradox whatsoever. There never was. Anyways, I'm going to stop it there. Maybe commentate on the rest later.